Okay, let's see what activity 4, distance and accumulated change, is about. So you're getting into, you're given a rate, and when you find the area under the rate, that is an amount, right? Or distance, or the number of people in a population, the amount of milligrams in somebody's body versus on the rate that it's going in. All right, so fill in, after the test. So I know this is scary looking, but for right now, don't worry too much about the, well, I lost my thing, the screenshot here. Don't worry a lot about the left side here, but let's grab this, and let's go rock chair, And this is important that you understand all these pieces. I know you like to just go jump straight to, well, let me just do this stuff. This is later, okay? This is antiderivatives. The first part we're looking at is this piece right here, where all this is saying is if I have a graph, so let's say my graph looks like this, and I want to find the area underneath the graph, then what I'm doing is I'm taking the height, which is the f of x, so that's the height of the graph, and then times the width of this rectangle. Okay, so that's what that change in x is. So that's what you're doing. I mean, you're actually just finding the the area of a whole bunch of rectangles, and we'll find out later that this is the exact method, where this is the approximation method. Okay, and you're going to see this little formula here is good to know if you want to be able to find the change in x, b minus a over n, where a is the beginning of the interval and b is the end of the interval. And then n is the number of intervals or number of rectangles, okay? But you can manipulate this if you know algebra, right? I didn't really want to say that, but that's what I meant. You can flip these around if you want to find the number of subintervals. All right, so let's see what we got going on here. All right, so this first part is just getting you to see, I know it's like, wee, this is so much fun, but it's just getting you to understand that, and it talks about it here, that this is a rate, and we are looking at the area, okay? So underneath this line, which is a rate, we are trying to find this area. So this rate is given in, I believe, what, miles per hour, and so the part that's gray would be the miles that this dog travels. And that's all this is going through. Okay, so you can read through all those slides. Okay, so if we have something that is not nice and rectangular that we can draw, we can get exact area, this is where we need these rectangles, these Riemann sums. So let me get this up here, left, right. What I'm looking at is what corner of the rectangle this is touching. So that's obviously a right. You have to click on them to zoom in. This looks like that's a right, but that's all I'm doing on these is I'm looking to see this is a left, that corner. So I'll let you finish those cards up. Okay, so it says we'll have a little bit of review. Will a lower sum start with the first value of a table? This is not always, because if your values are high and they're going low, so this is a sometimes, and that's what I'm showing here. Notice this first table would be a lower sum because these values are lower. Students always ask, well, how do I know which one's the lower and which one's the upper? Well, it's the lower value, right? What I do is I look at the first and the last value. If the last value is lower, okay, so in this case, if I started at the left, this would be an upper sum. So you always have to, look at those values. All right, so here it's asking me what's A, what's B, N, and the change in X. Well, your wonderful teacher made this easy for you. If you know A is the starting point at 0 and B's 15, you know the answer. Okay, but let's just talk it out. A is the starting value. Okay, so as you saw me draw so ugly here, it's the starting value of the area you're looking for, and B is the ending value. The change in X, how is it jumping by threes? 0, 3, 6, 9. How many intervals are there? Subintervals, rectangles, that's the N. 1, 2, 3, 4, 5. All right, so that's how, you need to know all these pieces, because when we get into building these into an equation, we need to know, of course, what to put where. All right, it says, suppose you want the approximate area between the x-axis and this derivative, which is, it says do not type. See if if I could read, do not type that. So I am doing 2 square roots of x. If you can type that in, it will make all this stuff open. All right, so now from here, it's giving me all this information. And once again, I would like to, I would like to screenshot this so I can kind of write it out for you in a better picture. All right, so some of the key things here that I see is, of course, this graph right here is my f of x equals 2 square roots of x. That's my graph. This is very important. My A in this case is 4. That's my starting value. My B is 25. So I actually could go ahead and put those here in the table, 4 and 25. But how do I get these values here in between? Well, it says using 3 rectangles of equal width. That's N. So N is 3. Remember that formula where I can find my change in X equals B minus A over N. So it looks like 25 minus 4 over 3. 25 minus 4 is 21, divided by 3 is 7. So this is going to jump by 7s. So 4 plus 7, 11. 11 plus 7, 18. And guess what? 18 plus 7, you better get 25. And I can check this with my jumps. 1, 2, 3, my 3 subintervals. Now these values, you're just plugging this into the calculator, and I think I have my calculator here somewhere. So it was 4, 11, 18, and 25. So if I get my I don't like that calculator. I like this one up here. If I get my calculator going, so, well, I don't think I need to do 2 square root times the square root of 4. So the square root of 4 is 2. 2 times 2 is 4. Woohoo! Got that one right. This one I think I need 2 square roots of 11. And somewhere it probably tells me how to round to 2 decimal places. So 6.63. Woohoo! 2 square roots of 18, which would be 8.49 rounded, and then the square root of 25 is 5. 5 times 2 is 10. So I can plot those points. So what you're doing now with this graph to be able to draw these out, okay, so if I want to actually draw these out, I guess I'll try to do it with a straight line, is if I'm doing a left rectangle, then I am going to start at 4, okay, on the left-hand side. And then what I do is I tend to draw all these straight down. That should hit 11 because of my table. This should hit 18. And then you're going to see, I'm not going to draw that one straight down. And then I go straight across. So there's 1 rectangle, 2 rectangles, and wasn't N equals 3? Oops, I went a little bit too far. Undo that. And so I should stop right there and come straight down. So this madness here is going to be my left rectangle. Why again is it a left rectangle? Because see that big old bad boy? It's on the left corner. So if I want to do a right-hand rectangle, so now I go up to this value, and it's kind of weird. You go to the left, but notice the right corner is what's touching. So I go up here, I go here, I go here, and now I actually go to this value. I go there, I go there. Don't judge that I can't draw a straight line. And so now that's all this area. Oops, that was ugly, but you get the picture, okay? So that's what I'm looking at. And so this next slide here is going to ask me now, based on my ugly picture, how can I approximate this area? Well, I need these values of my, what'd you do that for? I need these values of my table right here. Let's just go ahead and grab the graph so you can see it in here as well. We got way too many tabs open. And so if I want to find, the left, which is going to be a lower sum because it's below that red line. Remember that this is, I lost my pencil. This is the graph that I'm looking at, and the left is going to be a lower sum. I would start at this first value, and I would add all of those up, and I would multiply by what? 7, because the change in x, remember my change in x equals 7. So I would take 7 times, this is where you could do each one, but I tend to add them. I think it's easier to do it like this, plus 8.49. And so if I go back here and here, I can take 7 and then add my 4 plus 6.63 plus 8.49, and I get 133.84. 133.84. We all knew that I rocked. Did not need Desmos to tell me that. And then you're going to just do the same thing, but instead of starting at 4, you know, looking here, you're going to start at 6.63, add 8.49, and then add 10. So I will leave that up to you to finish that. All right, so if you understand the symbols. Oh, so what this is, I always, and in fact, I've posted this in GroupMe, but I get this asked all the time, is let's say that you're given a table like this. And so if I look at this and I break down all the different pieces, I can see the change in t is 4. How do I know that? 0, 4, 4, 8. See how it's jumping by 4s? You add 4. What is n? 1, 2, 3, 4. Sorry, n is 4 as well. Okay, just to be complete, a is 0 and b is 16, the start and the end. Okay, so it says, looking at the table, if you used n equals 2. Well, how the heck do I do that? What I do, so it's telling you you want 2 subintervals, meaning 1, 2. I hide these values. You're not going to use them. So now my change in t looks like it was 4, but it's now 8, because I'm jumping by 0 to 8 and then 8 to 16. All right, what else we got there? Oh, this is just getting you to see the more rectangles you add, definitely the better it is. All right, so that with the Riemann sums is all approximation. We want to actually get exact values, and so we want to be able, and this goes back to this slide right here that I said don't worry about this yet. Well, guess what? Now you're going to worry about it. We are going to get area eventually in the next Desmos, but in this activity, all you are going to do is you're going to go through the shortcuts. Okay, so notice, go back here, notice the power rule. This is a power. It says to add 1 and do the same on the bottom. So if you have x squared, then it looks like this would be x cubed over 3. I think I have to do plus c here. Let me see. Woohoo! Got that right? Because notice, this is the power rule. And if you don't know these yet, because this is brand new, right? I don't expect most of y'all to know these yet. You know what you could do is just put anything in here and submit it, and then it'll show you which rule you should be using. So this looks like this bx to the fourth over 4 plus that constant that we don't know about. High five. Sine of x, if I don't remember how to do it. Okay, so it's negative what's in here. So negative 1 over 3 cosine of 3x plus c. These are all just practicing. E to the 3x, this is actually, and if you think about it, the chain rule, you put a 3 out front, right? So why are we putting a 1/3 out front? Well, because if I take the derivative of this, that k will come here and cancel. And you're working backwards on these. All right, so I'll let you get through all of these. You don't recognize this. This is the ln. Okay, be sure you put the absolute values in there. See what else we got. What rule? This one's funny because students always put ln, but go back and remember you could bring this up, x to the -2. So I think that would be a power rule. Okay, and so I'll let you do that. Yeah, you should have chosen the power rule. And now we get to this example here. So it says blah, 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 blah. Suppose that bacteria grows at a rate. This value right here is a derivative at a rate. Okay, so this is the rate. Suppose when t equals 1, the population is 25,000. Find the function. So we have to find the function, which means I need to find this antiderivative. Okay, my thinking is because that was given to me as a rate. And so let's see if I can do this bad boy. Let's go here. We'll take dude with us so we have a nice little image here. All right. So the first thing I see is a fraction, which we all love to hate. So what I tend to do, so I'm doing this, right? I'm doing this antiderivative. And I don't remember anything with a square root, so I don't know what to do. I'm going to pull that 5,000 out front. And then I'm going to bring the square root up to the top. Okay, so that's going to be the first thing I'm going to do. Remember, this on the bottom is the same as the 1/2 power. And when you bring it up, it becomes a negative. So now this is just flat out a power rule. So I still have that 5,000 out front, but now I'm going to do t to the -1/2 plus 1. -1/2 plus 1. So sorry, I got to go this way. So I have 5,000 equals, looks not equals, 5,000 times t to the 1/2 over 1/2. Remember, when you divide fractions, you can flip and multiply 10,000 t to the 1/2, or if you like it better, square root of t. And I think you better put plus c. So 10, 1, 2, 3, square roots of t plus c to get that right. Great job. And then here what's happening is it says, suppose when t equals 1, the population is 25,000. And if I was better at writing this, and I should be, you should write this as an actual function. This function is p of t equals, and this is big P of t, equals 10,000 square root of t plus c. So what it's telling you to do now, it's saying to let t equal 1, and I don't remember what the number was, 25,000, set this equal to 25,000 and solve that for t. So that's what you're doing there. Let you get that one done. And so you plugged in t equals 1. What do you get for c? And then now I can actually, I kind of cheated, right? Because I can see right there that c is 15,000. Okay, but you need to know how we got that. We let t equals 1, set this equal to 25,000, all that. Now here what you're doing, it says how many days. That tells me right now I need to solve for t. So you let this equal 115,000 and then you solve it for t. Hopefully you can do that algebra. If not, ask me questions. All right, that is Desmos Activity 4.